Okay, so today we cover section 7.4, integration. By partial fractions. So, to motivate, I start with an example. Okay, let's suppose that on the left we have negative 1 minus 1 over x plus 3 plus 2 x minus 4. Okay. Tell me, is this a function that is easy to integrate or not? If I were to integrate this, is it easy or not? So you can see that it's a sum of two terms. Let's look at the first term. What's the integral of this? Something like, it's a log, right? It's a log of x plus 3. What's the integral of this? It's the log, 2 over log of x minus. So it's very easy to integrate. Now I'm going to multiply through and get it to a common denominator. Okay? So what do I get? Minus x minus 4 plus 2 x plus 3 x plus 3 x minus 4. And I open the brackets. Okay, and I simplify. Okay, so this obviously is equal to this. Now look at this function. Is this easy to integrate? Would you know immediately how to integrate this? No, right? You would have to stop and think, what do I do next? So on the left we have something that is very easy to integrate. On the right we have something that we don't know how to integrate. And they're the same. Okay? So that working backward, that gives me a very good method to integrate something like this. So let's write it down right away. The integral of the right-hand side is equal to the integral of the left-hand side which is very easy. And I'm done. Right. Only if I knew to begin with how to represent this fraction as something like this, I would be able to integrate all such examples. And this is where we have the method of partial fractions that we're going to cover today. So we will consider functions that look like this. P of x over q of x. P and q are polynomials. Okay, polynomials. And as you can see, this is an example of such a function. We have a polynomial of the first degree on top and the polynomial of the second degree at the bottom. So we're going to need the notion of a proper fraction. Means that the degree of P is less than the degree of Q. Okay? So is this a proper fraction? Is this a proper fraction? The degree of P is 1, the degree of Q is 2, so it is a proper fraction. Now, if we are given an improper fraction, we can always reduce it to a proper fraction. Any fraction can be reduced to a proper fraction by long divisions. So this is something that you should be able to do, to divide one polynomial by another. So for example, let's consider x cubed plus 2x minus 4 x minus 2. So you can see that this is not a proper fraction, because here the degree of p is 3, and it's greater than the degree of q, which is 1. Not a proper fraction. So we can use long divisions to reduce to x squared plus, wait, eight plus 8 over x minus 2 plus x squared plus 2x plus 6. Okay. So you will be practicing to do this at the discussions. Okay, and you can see that there is something, that there's a polynomial, which is very easy to integrate, plus a proper fraction, which is also easy to integrate. And the methodology will be worked out at discussions. So now, today we'll go through 4 cases of partial fractions. And they go from easy to hard. So case 1 is when q of x is a product of distinct linear factors. So let me keep track of them here. One is distinct linear factors. So an example, so to classify all these things, we always look at the denominator of a proper fraction, and we try to factor it into linear multiplier. So for instance here, we have a degree 2 polynomial, and somehow we were able to factor it into these two. And so this comprises the main idea of the method. So let's look at an example to make this all very clear. So let's suppose we are given the following fraction. Is this proper or not? So the degree of p is 1. The degree of q is 3. So it's a proper fraction. Okay. So we don't have to do anything. Now let's consider the denominator and try to factor it out. So you can see that x multiplies everything. So I put x here, and I have 3x squared minus 5x minus 2. Now it's a quadratic polynomial, and everybody knows how to, decompose this into factors. We just have to find the roots, right? So I'll skip one step here and write down the decomposition of this quadratic polynomial. If I find roots of this, I'll get minus 1/3 and 2. Okay. So you can see that this is a product of 3 distinct linear factors, and that's what classifies it as the simplest of cases. And we will have other cases a little bit later. So the next step is to write it in the following way. So our given function, now I'm always going to write it like this to make explicit the 3 linear factors. I represented as the following decomposition. And it can be shown that you can always find constants A, B, and C to make this an identity. So our task is exactly this, to find A, B, and C. And the next step is obvious. This has to be equal to this. Right has to be equal to the left. So I bring the right-hand side to a common denominator. So in the denominator, I'm going to have the product of the three factors, just like on the left. And in the numerator, I'm going to have the following combinations of coefficients. Okay. So I have to find numbers A, B, and C to make the right-hand side equal to the left-hand side. The denominator is already the same by construction. They're going to be the same linear factors in the denominator. The numerator is the problem. Right? How do we make them the same? There are two methods of doing it. So I'll start with the simpler method. So the simpler method doesn't always work. The more complex method always works, but it's a little bit more involved. So simple method. I'm going to set x equals 2, for instance. X equals 0. So this numerator has to be equal to this numerator for all values of x. Right? The two functions have to be the same. So the equality has to hold for all values of x. I'm going to pick 3 values of x that make this equation really easy. Okay? So the first value is x equals 0. And why is it easy? See, the first factor, let's not talk about it for now. This one is 0, because x equals 0. And this is 0. So on the right, I just have a 0 minus 2, 3 times 0 plus 1. Or I can say that this is minus 2x, minus 2a. And that's supposed to be equal to the left-hand side, which is 0 plus 3. So this is a very easy equation for a, see, because many things canceled. Like these two whole terms canceled. So that gives me a equals minus 3/2. Okay. Then what are other good choices of x to take to make this really simple? 2, right? Because if x equals 2, this one is killed. And this one is killed. The only remaining factor is this one, right? It's 0. We choose x in such a way as to kill as many of these as possible. So x equals 2. So I have 0 plus b times 2 times 2 times 3 plus 1 plus 0 equals, left-hand side is 2 plus 3. So let's rewrite this equation. This is 7b times 14 is equal to 5. Therefore, b is 5 over 14. So I solved for b. The last one was the last good choice for x, minus 1/3. By the way, you can always determine these easy values by looking at the roots of the original denominator. What are the roots here? 0, 2, and minus 1/3, right? And this is 0, 2, and minus 1/3. These are the ones that work. Any other choice would also work, but make the math a lot harder. So this is a clever choice of the values of x that make the calculations the easiest. So when x is minus 1/3, the first and the second terms are 0, and I have c times minus 1/3 times 1 minus 1/3 minus 2 is equal to 8/3. So c is 24 over 7 if I solve for this. Okay. So what is the result of this calculation. The given integral x plus 3 dx 3x cubed equals the integral of the partial fractions. So I substitute minus 3/2 over x plus 5/14 over x minus 2 plus 24/7 over 3x plus 1 dx. And you can see that this is easy. It's just a sum of 3 logarithms. Minus 3/2 log x plus 5/4 log x minus 2 plus 24/7 log 3x plus 1 plus c. Questions?
Should it be log of 3x plus 1 over 3?
3x plus 1 over 3. You're right. Thank you. So what's that other method that I didn't mention here? So the first method, I just look for convenient values of x and write down 3 equations. So the more general method is as follows. I look at the right-hand side, okay, and I rewrite it by multiplying everything through. So I'm going to have a quadratic equation for x here. So 3x squared plus x minus 6x minus 2 plus b. I multiply all the x's, right? 3x squared plus x plus c x squared minus 2x. Now I simplify a little bit. So this is 3x squared minus 5x minus 2. Nothing else to simplify. And now I want to collect the coefficients in front of each power of x. So I have a second power of x, I have a first power of x, and I have a 0th power of x. So in front of x squared, what do I have? 3a. Here I have plus 3b plus c. Okay. In front of x, I have minus 5a plus b minus 2c. And in front of 1, basically terms that don't contain x, I have minus 2a, nothing here, and nothing here. This has to be equal to x plus 3. So now I compare the powers of x. What is the coefficient in front of x squared here? Obviously it's 0, right? So the coefficient in front of x squared has to be 0. So my first equation becomes 3a plus 3b plus c must be equal to 0. The coefficient in front of x has to be 1. So my second equation is minus 5a plus b minus 2c is 1. The coefficient in front of the term that doesn't contain x must be equal to 3. So minus 2a is equal to 3. So this is a system of 3 linear equations, okay, that I can resolve. For instance, the last equation actually gives me minus 3/2, which is the same as I obtained by the simple method. From knowing a, I can solve these two. It's a little bit more involved, but it always works, okay? So it's your choice which method to choose. Students usually prefer the simpler method. Okay? Fine. So this shows you an example of a fraction whose denominator consists of distinct linear factors. So what else can we have? In the second case, so case number 2, we can have linear factors, some of which are repeated. Okay. So here's an example. First of all, we established that this is a proper fraction. Question?
Yeah, I'm just a little curious. The three equations that ended up defining what the values were, how did you come up with those?
Okay, so first I multiplied this whole through and collected the powers in front of x squared, x, and 1.
Okay.
And this is supposed to, again, be equal to the left-hand side, x plus 3. So this is a polynomial in x that contains, so this is the coefficient in front of x squared. This is the coefficient in front of x. This is the remaining coefficient.
Okay.
It's supposed to be equal to this. On the right, the coefficient in front of x squared is 0. Right? It doesn't have x squared. X plus 3 does not have x squared. So formally speaking, we can say that it's 0 times x squared. So this coefficient in front of x squared has to be equal to this coefficient in front of x squared for the two functions to be exactly the same.
So each individual one has to be equal to that part?
So we view the right-hand side and the left-hand side as polynomials in terms of x.
Okay.
And we equate the coefficients in front of equal powers of x. Okay. And once I'm here, I put my second case here, repeated linear factors. So let's go to our example. It's easy to see that this is a proper fraction. Second power divided by third power. So we're good here. And let's write down the denominator and try to factor it out. So again, x comes out. And what's left is this polynomial. So there are two ways to deal with this. You can either look for roots of this, or you can simply recognize this as a full square. So it's x times x minus 2 squared. If we were to look for the roots, we would have two roots that are the same. Question?
Isn't this supposed to be x squared minus 4x?
Yes. Oh, thank you. Thank you very much. Thank you. So there are going to be two repeated roots, which are 2, and this results in this combination. So we have a factor of x and two identical factors, x minus 2. So if I blindly use the previous method, what would I do? I would have to say that x squared plus x minus 1 x minus 2 squared. Let's represent it as partial fractions. So the first one is a over x plus b over x minus 2. But what else do I put there? Okay. If I blindly use the previous method, I would have c over x minus 2, because these are two factors. And as you can see, these are the same. So by redefining a new b to be equal to b plus c, I would just have this combination. And then when I bring it to a common denominator, I would be missing 1 power of x. Okay, so it simply doesn't work. I don't have enough different denominators to use the old approach. So instead of this, we do the following. Okay, this is the method. We have as many terms containing x minus 2 as they are factors x minus 2. For instance, if we had x minus 2 to the power 7, what would we put here? b over x minus 2 plus c over x minus 2 squared plus d of the same thing cubed and so on up to the power 7. So we would have 7 terms all containing different powers of x minus 2 up to the highest power that we have. In this simple case, we only have 2. So we have 2 terms corresponding to x minus 2. Okay? So this is a modification of the method when we have a repeated factor. The non-repeated factor comes just as before, separately with its own coefficient. Okay, so now let's go through the calculations. We are going to bring this to a common denominator. Like this. And we will have to make sure that the numerator on the left is equal to the numerator on the right. I'm going to try easy values of x. Okay, what are easy values? The first one is obvious. It's 0, right? So what do I have? A times 4, and these two are killed. Okay, equals, on the left I have 0 plus 0 minus 1. So A immediately comes out as minus 1/4. Okay. Now, what's another good choice? 2. So this one is 0. This one is easy, also 0. C times 2 equals 4 plus 2 minus 1, 6, 5. So C is 5/2. Excellent. And I ran out, right? There is no other root. So what do I choose? Usually, I suggest you stick in something that looks easy. Okay, just try 1 or minus 1, something like this. It's not going to make any of these 0. Okay, you don't have enough different roots that make them 0. But it will make them look nice and easy to operate. So if we take x equals 1, what do I have? A plus b, actually with a minus b plus c, not so bad, equals 1 plus 1 minus 1, 1. Okay, so this equation can be solved because I already know a and c. So minus 1/4 minus b plus 5/2 equals 1 gives me b 5/4. So these are my coefficients. And I can write down the resulting integral. Minus 1/4 over x plus 5 over 4 x minus 2 plus 5/2 x minus 2 squared dx. Is this an easy integral? Yeah, it's not so bad. We're going to have a couple of logs and something else. Something else comes from this power, right? So let's do it. Minus 1/4 log x plus 5/4 log x minus 2 minus 5/2 x minus 2 plus c. Done. Okay. So again, to practice, what if I have, I don't know, x squared how would I represent such a fraction? You can see that it has two different linear factors, each of them repeated. So I would have to write the following. A over x minus 1 plus b x minus 1 squared, and that's it for x minus 1, there are only two of them, plus c x minus 2 plus d x minus 2 squared plus e x minus 2 cubed. Three of those, three terms for x minus 2. Questions? Question?
How did you make it a common denominator for that part?
This one? So the common denominator, I have a factor of x and two of these. So the common denominator is x times x minus 2. So what is this one missing? It's missing x minus 2 squared, right? To have the same denominator as this. This term is missing x minus 2 squared. This term is missing 1 power of x minus 2, and it's missing x. And the last guy is only missing x. Okay, so that's all it gets. More questions? Okay, so it gets worse. So case 3. And let me start with an example. Let's look at x dx. X squared plus x plus 1, x minus 1. Okay, what is this? It's a proper fraction, power 1, power 3. And you can see that we have a linear factor here. So let's look for roots here to factor this one into two linear factors, x squared plus x plus 1. So as you can see, it has no roots, right? There is no value of x that makes that 0, which means that I cannot write it as a product of two linear factors. This is all I get. I cannot simplify or factorize it anymore. So that's why this example fails to be a product of linear factors. It has a nonlinear factor. Okay, so we call this non-repeated nonlinear factors. Non-repeated is because we only have one of those. If it was squared or third, that's the next case, even worse. So this one has to remain like this. So what do we do? We know exactly what to do with the linear factor. It's just this. It's always like this. Now, I have to put this whole thing in the denominator. The difference is that because this is a quadratic factor, I don't just have a constant here, but I have a combination b x plus c. So if I have a quadratic factor, in the numerator I have to use a linear function. So it actually gives me two coefficients. And you notice that the number of unknown coefficients always has to coincide with the degree of the denominator. So here, for instance, I have a third degree polynomial, one from here, two from here. So I have three coefficients, one, A, B, and C. Here in the previous one, what did I have? Again, this was a third degree polynomial. So I have A, B, and C. In the example I just erased, there were two powers 2 and 3, so altogether it was 5. So I had A, B, C, D, E, right? So the number of unknown coefficient has to coincide with the degree of the polynomial. And here, if I just had one constant here, I would only have two unknown numbers. I need to have 3, so I make this a linear function. The rest follows the same algorithm, at least as far as determining the coefficients goes. We have something new as the next step. But for now, we multiply through. Okay, and we test some values of x. So one obvious choice is 1, and it kills this guy. So we have x a3a equals 1. So a is 1/3. Linear factors are always very easy. Okay, and that's it. No other roots, because this one, it doesn't have roots. That's why it's not a linear factor. So what do? I take 0. 0 is always a good choice, right? It makes everything simpler. So for a, I have coefficient 1, and I have c times -1 equals 0, which means that c equals a is 1/3. So I found c. It's easy. Another choice, arbitrary but simple, is -1. You can take any other. You can take plus 173 if you like. It will give you the right answer, but the calculations will be horrendous. So you try to do something simple. So with -1, I have a times 1 plus b minus 1 plus c. Okay. Minus 1 plus c, wrong brackets, equals -1. So I already know a and c. 1/3 minus b plus 1/3 equals -1. I can solve this, hopefully. That gives me b equals -1/3. So I found all the coefficients. And I can rewrite my integral in a simpler form. So let's do that. So x squared plus x plus 1, x minus 1 becomes equal 1/3 x minus 1 dx plus b dx. Okay, so these are my two terms. Question?
I think you missed the last part, C of the x minus 1.
I missed.
Yeah, because don't you multiply by -2
To the bx plus c. Or x or negative 1.
So, yes, -2. Okay, so the answer is probably correct, and it's probably a typo. Let me know if this is incorrect, if the answer is incorrect. Okay. So what do we deal with here? This is known. We know exactly what this is. We're going to do them step by step. So this is 1/3 log x minus 1, and we don't have to worry about this until we arrive at the final answer. Now consider this integral, minus x plus 1, x squared plus x plus 1 dx. Okay, so this is the harder one. It's still doable. So one way of doing it is to use substitution. So I suggest we take u to be equal to this whole denominator, x squared plus x plus 1. Okay, and we immediately calculate du, so 2x plus 1 dx. And what I want is minus x plus 1. What I get is 2x plus 1. So let's multiply it by minus 1/2. So minus 1/2 du Question? Oh, I'm sorry. Yes. So u is x squared plus x plus 1, 2x plus 1 dx minus half du is minus x minus 1/2 dx. I'm trying to obtain minus x plus 1 from my differential. And I'm failing a little bit because I have minus x minus 1/2. But I can do this. I can say minus x plus 1 minus the 3/2, right? dx. So I have the part that I want, and I have an extra constant factor, right? So what does this give me? I have minus x plus 1, x squared plus x plus 1 dx equals minus 1/2 2 divided by u, okay, and I have plus 3/2 dx x squared plus x plus 1. So this part goes here, and this part comes here. Question?
Yeah, where did the 3 have come?
This? So I have minus x minus 1/2, and I want minus x plus 1. So I'm forcing it to be minus x plus 1, but as a price that I pay, I have to subtract minus 3/2. Okay? So it's kind of forcing it to be what it should be, and then paying the consequences by having this extra term. Okay? So let me do these two separately. This one is really easy. Minus 1/2 log of u is minus 1/2 log of this whole thing, x squared plus x plus 1. Actually, I can forget the absolute value because this guy is always positive. Okay, so this is very easy to take. How about this term? So with this one, I can recognize it as something that looks like the antiderivative of the arctangent. For the arctangent, remember, I have to have x squared plus 1. Here I have something else plus 1. So I have to complete the squares. So complete the squares. So I have 3/2, okay, dx, and here I have x squared plus 1/2 times 2 times x plus 1/4 plus what is missing is 3/4. I complete the squares in the denominator. 3/2 dx x plus 1/2 squared plus 3/4. Completing the squares. Now I want this to be 1. So I go 3/2 dx, and I take out 3/4 here. And I get x plus 1/2 squared divided by 3/4 plus 1. So now this guy is going to be my new variable. Square root of this is going to be my new variable. One more step. 3/2 dx 3/4. And here I have 2x plus 1 over square root of 3 squared plus 1. Okay. So this is the same as the original one, where I factored out a full squared plus 1. Okay. And now you can see that the substitution u, 2x plus 1 over square root of 3, gives me the desired shape. So du is 2 over square root of 3 dx. So I get 2 du times square root of 3 over 2 u squared plus 1. You can see that now it really is an antiderivative of the arctangent. And this is what I had to recognize from here. And such examples come up all the time for case 3. So I have to integrate something like a constant divided by this irreducible quadratic factor. Question? I can't hear.
How did you get 2x plus 1 divided by
2x plus 1 half? Did you ask me about
U.
this one?
Back. Top.
How do you do this? This one?
E.
Okay. I had to present this as the square of something. So I had to take a square root of this. What's the square root of this? It's x plus 1 half divided by square root of 3 times 2. Okay. And this is what comes here.
Why is it still squared? That square root of it?
So I have, let me write it out. X plus 1 half squared over 3, 4 equals square root of this squared. So first I take the square root, and it's squared that, right? So to figure out a way of writing it as a square of something, I have to take a square root of it and make a square out of it. So this is the operation here. So I'm going to leave the square here and take the square root. X plus 1 half, and I have 2, and I have a square root of 3. This is what I have here. So I'm very close to finishing this. So I have 2 times du square root of 3. What's the antiderivative? This is, of course, square root of 3 over 2 arctangent of u. And that is square root of 3 times arctangent of my definition of u. This is 2x plus 1 over square root of 3. Now I have to put everything together. So I have 3 pieces to this puzzle. What are they? This guy. And I have this guy. And I have this. And I need the factor of 1/3 in front. Okay. So all together. So this is the third part times 1/3. So altogether, I have 1/3 log of x minus 1 minus 1/6 log let's see. Okay. So it's not an easy integral, and this is how unless you have some exception, you're always going to be able to. You're always going to take an integral of the quadratic factor alone, a constant divided by the quadratic factor. Okay, and it always comes out to be an arctangent, as long as you complete the squares. Now, to finish, what is the fourth logical case? Repeated nonlinear factors. And I will ask the TA to cover this at the discussion. This lecture never fits into the lecture, so we'll always have to do that. Thank you.